let us start the next type of flow, basic flows or elementary flows, that is source and sink flow. Okay. See, first of all, what is this source? To be more precise, we will be calling it as plain source and similarly plain sink. What is that? Why I am calling it as plain source? Because I am going to describe it only in a xy plane. Okay, I'm not going to consider the third direction. Okay, so almost all the elementary flows which I am discussing, we are going to discuss a plane flow only, that is in 2 dimension only, there is no third dimension for it. So what actually this plane source indicating? First of all, let me give you source, then I will go for sink. Plane source is something, it is a point, okay, it's a point from which fluid will be emerging out, or fluid will be continuously flowing out. Okay, fluid will be continuously flowing out from the point, okay, from one single point in all the direction. And the important point to note here is at a constant rate. Rate here means it may be a mass flow rate or it may be a volume flow rate. Okay, so let me just show you that. Okay, so it's a plane, so it's a point in a plane. Okay, so in a plane, it's a point from where fluid is emerging or fluid is just coming out from that point in all direction. Okay, so in all the direction with a constant rate. Rate may be m dot or it may be q. Okay, either it is discharge or mass flow rate. But this is just a simple definition. You could see here from point 1 in all the direction the fluid is coming out. Okay, so in all the direction fluid is coming out. More precisely, if the fluid comes out from a single point in all the direction, what I can say about radial velocity and tangential velocity? Was there any rotation of the fluid? Nothing. So tangential velocity is 0. Was there any radial velocity? Of course, fluid is coming only in radial direction. Okay, so Vr is not equal to 0, but tangential velocity, we will take it as v theta, which is equal to 0. So this is more specific one. Okay, so if this is something where a point from where fluid will be continuously emerging out at a constant at a constant rate, such that the radial velocity is not equal to 0, that is, it will have some radial velocity, but tangential velocity is 0. Okay, now let it be, but we need to have some more clarity about this. To be honest, this is, I'm talking about a point, right? A point from where fluid is emerging out. But in reality, it is not a point. In reality, it is a line, something like this. Okay, it's a line, something like this. From the straight line, fluid is coming out. Okay, from this straight line, fluid is coming out. Okay, in all the direction. So this straight line is said to be source. Okay, if it is sink, of course, if it is a straight line, just listen, if it is a straight line, if you see from front side, okay, if you see from front, it's obviously a point. Okay, so that is a straight line in a plane, it will look like a point only. Very obvious, straight line in a plane will look like a point. So that is why plane source, okay, so plane source is something from where, plane source is a point from where fluid will be continuously emerging out at a constant rate. A constant rate means it may be mass flow rate or volume flow rate. But in actual sense, it is a straight line from which fluid is emerging out, okay, in all the direction. Provided all the mass flow rates and volume flow rate should be calculated per unit length, which means I need to consider this line, okay, I need to consider this line is of 1 meter only. Okay, so I need to consider this line is 1 meter only. So a line of a unit length from where in all the direction fluid is coming out, in radial direction, of course. What is sink then? Simple, just opposite. Sink, all flows, all fluid will be entering inside in radial direction. Again, there also there is no v theta, only Vr, but all the fluids will be entering inside. So it is a point in which all the fluids will be flowing inside. Okay, so by maintaining constant rate. First, let us talk about source. Later on, sink is just you need to change the sign. That's it. Okay, if you get something plus in source, in sink it should be minus. If you get something minus in source, then in sink it should be plus. That's it. Okay. So to start with, first, before entering into our streamlines and velocity potential line, let us understand 3 important things or 3 important factors or 3 important terms, okay, in source and sink. The first term is mass flow rate. Okay, so how to define or how to write formula for mass flow rate here? Generally mass flow rate is nothing but density into area into velocity, but in this case there is only one velocity. What is that? Only radial velocity. And how the fluid is flowing? Only in radial direction. So what should be my area? So when the fluid is flowing only in the radial direction, my area will be something like 2 pi r will give me perimeter, and if I multiply with the length it will give me surface area. So I need to take surface area. So mass flow rate will be rho surface area into radial velocity, because fluid is leaving, right? Fluid is leaving radially only, so I need to take surface area only. And what is my surface area here? I already said that I am going to take for per unit length, right? I am going to take per unit length, so length will be 1. So simply this is going to become rho into 2 pi r into Vr. So this is my m dot, and what is the term called as mass flow rate per unit length. Okay, fine. Now what about discharge then? Simple. Discharge is area into discharge or volume flow rate is area into velocity, and in this case area I need to calculate per unit length. So this will become 2 pi r into Vr. Okay, so this is Q, which is volume flow rate, okay, or discharge per unit length. Now there is one more thing to what I could say to define. Okay, so that is K, okay, which is strength. Okay, so if I talk with respect to source, I will say that it is source strength. If I talk with respect to sink, it is sink strength. Okay, so first we will concentrate on generally strength. Strength is nothing but mass flow rate. Okay, it's a ratio of mass flow rate with respect to density into 2 pi, or in other word, volume flow rate by 2 pi. Or simply you just bring that rho into 2 pi this side and 2 pi this side, what I will be getting? R into Vr, right? R into Vr. If I bring rho into 2 pi this side, RVr. If I bring 2 pi this side, RVr. So this is simply Vr into R. Okay, so this is strength. Okay, so if I talk with respect to source, it is source strength. If I talk with respect to sink, it is sink strength. Okay, and now what does this means? Somewhat you could find out. If the radial distance, r is radial distance, right, from here somewhere, okay, somewhere radially. So if radial distance from the source, okay, this point is my source, this point is my source. So from the source, if the radial distance was 1 meter, then the radial velocity will be equal to k. Simple from the formula itself. If radius becomes 1, if radial distance become 1, k is equal to Vr. So how to define the strength of a source or strength of a sink? Simply strength will be equal to its radial velocity if its radial distance from the source or sink is 1 or unity. Okay, if radius becomes unity, the relative velocity, radius becomes unity, the radial velocity will be strength. Okay, so you need to note down these 3 things. And now one more thing also, we already know that these 2 has to be constant because that is as per the definition. Now strength should also be constant. How you are getting to know that? Because m dot is constant already, okay, in a source flow or a sink flow. Density is incompressible, we are taking all flows are incompressible only. 2 pi is a constant. So numerator constant, denominator constant, so k will also be constant. So for a source flow or a sink flow, k value will remain constant in that particular flow field. These are some, what I could say, some introduction which is required. Now we will jump into streamline and then path line. We will find out how does the flow, how does the flow net looks. Okay, now let us proceed for this stream function and velocity potential function. We already know that in polar coordinates how does stream function and velocity potential function looks, and this is how it looks. First let us take stream function. Okay, so in radial velocity can be written as 1 by r into dou psi by dou theta. Similarly v theta, that is tangential velocity, can be written as minus dou psi by dou r. We already know that for a sink or a source flow, I am going to discuss about source only. So for a source flow, v theta is 0, right? So this becomes 0. Okay, if v theta becomes 0, we can clearly say that psi is not a function of r. Why psi is not a function of r? Because the first derivative is becoming 0. The first derivative becomes 0, then psi cannot be a function of r. Okay, right. Now similarly, let me take this, okay, that is Vr, which is nothing but 1 by r into dou psi by dou theta, and what I can do, I will just try to simply integrate it. Okay, so we already know that k is equal to m dot by rho into 2 pi, which is equal to q by 2 pi, which is equal to Vr into r. So Vr can be written as k by r, right? So Vr, which is equal to k by r, k is a constant. Okay, k is a constant in a particular flow field, source flow field. Okay, so that is going to be equal to 1 by r into dou psi by dou theta. This dou psi by dou theta, I can clearly write it as d psi by d theta, because psi now depends only on theta, it is not dependent on r. Okay, so which implies psi is only function of theta. I can cancel this r. Okay, then if you do the integration, psi will be equal to k into theta plus some constant of integration. Let me keep it as c1, but most of the cases we won't include that constant of integration, we will take the constant of integration as 0 only. Okay, so I'm just giving you the general equation, but as we proceed further, I will take the constant of integration to be 0. Okay, so this is our equation of a stream function. Okay, now if I want to find out constant stream function line, what I should do, simply this psi will become constant. If the psi is constant, already we know that c1 is a constant and we know that k is a constant. Okay, so that just now I said it. Okay, strength is a constant, so which clearly implies theta is going to be constant. See, theta constant line means what lines? Theta constant line means simply theta constant line means it's a radial line. Why? I will explain, just wait for a moment. See, just consider that theta is equal to some 30 degree. Okay, so theta should not vary. Okay, so constant stream function line or streamline is such that the constant stream functions are nothing but theta constant line. Theta constant line means radial line. What does it mean? For example, if you take theta, okay, theta has to be fixed for drawing constant stream function line. Theta has to be fixed for drawing constant stream function line. So obviously, if theta has to be fixed, the line, okay, the radial line which passes through this theta, that should be my constant stream function line. Let me show you there. Okay, so if I take my source here, let us consider this is our reference. Okay, so horizontal line is our reference, and if I'm saying that I'm fixing theta, okay, if I'm fixing theta for drawing constant stream function line, theta should be constant. If theta has to be constant, the only line is the radial line, right? So for maintaining theta constant everywhere, the line should be radial line and it represent psi constant. Similarly, I can get different psi. How? See, for some theta 1 I am getting psi 1, for some theta 2 I will get something like this. Okay, for some theta 2 I will get a constant, another psi line. Okay, let it be psi 2 is equal to constant. Similarly, for some other I will get something like this and something like this also. Okay, so all this are representing what? Representing constant stream function line. Okay, so psi is equal to constant. So psi is equal to constant line is simply theta is equal to constant line. Theta is equal to constant means it's a radial line. That's it. Now let us jump into velocity potential function. How does velocity potential function looks? Again, simple. V theta has to be 0 because in a source flow V theta is 0. Since V theta is 0, velocity potential psi is not a function of theta. As it is not a function of theta, instead of dou psi by dou r, I can write it as d psi by dr. So Vr is equal to d psi by dr. Already we know Vr is nothing but k by r, right? So I can take it, substitute it, integrate it, simply phi will be equal to integration of 1 by r is what? Ln of r. So k into ln of r. Okay, plus another constant, let it be c2. Okay, simple, right? So 1 by r's integration is ln of r, so k into ln of r plus c2. Where k is nothing but the strength of the source which is denoted by m dot by rho into 2 pi. Okay. Now, if I want constant potential, velocity potential line, which is nothing but equipotential line. Okay, if I want equipotential line, which is nothing but velocity potential is constant, then this has to be constant. C2 is already constant. K is also already constant. We know that. Okay, so in a source flow field or a sink flow field, K will be constant. So psi constant in the sense ln of R is constant, which can be written as R is equal to e to the power of some constant, which is another constant. Am I right? What I'm doing, I'm just applying exponential on both sides. If I apply that, R will be equal to e power constant. E power constant is also another constant, right? So simply, this is our equipotential line. So equipotential line means radius should be constant. For which line radius will be constant? It's not actually a line. For a circle only, radius will be constant. I hope that you understand the point. Okay, it's not a line. If I want to make radius constant, then it has to be a circle. For ellipse or for any other curves, it's not going to be, radius is not going to be constant. So simply R is equal to constant, that is radius equal to constant, indicates that it is concentric circles. Which is concentric circle? Equipotential line. So for a source field, equipotential lines are concentric circle. For and similarly, this is what constant stream function is a radial line. And how does it look there? Simple. For some radius, it will look like this. At some radius R1. Okay. So this is phi 1, and similarly, yeah, this is phi 2. This is phi 3. Okay, so you can draw it properly with your compass or something, but it has to be a circle. Okay, so this black color indicates equipotential line, and the red color indicates constant stream function line, and you could see very clearly both of them are when they are meeting, both of them are perpendicular to each other. Okay, so they will be perpendicular, they has to be perpendicular. Okay, now so you need to remember this equation, but most of the times we will equate C1 to 0 and C2 to 0, but there are some cases where the C1, C2 will also be useful. They might give some boundary conditions and they will ask. Okay, so we will discuss some problems. Already there are some problems which is asked in GATE XE itself. I'll be discussing it once after completing all the other flows also. Now here it is a source flow. So what we got the stream function is emerging out, right? If it is a sink flow, just opposite, stream function will be emerging in, and of course velocity potential function will be like this only. I will be giving you at the end. Let us continue our discussion on source and sink flow. So in this video, I'm going to discuss about how the pressure distribution is there in source flow. Later on, we will see how the sink looks, okay, that is sink flow looks. Then we will see the pressure distribution in sink flow also. See, the pressure distribution means it's almost same only, so it's not very much variation. Generally, what you will have is wherever minus is there, okay, in this equation, there it will be plus. Wherever plus is there in this equation, there you will get minus. Just the sign change will happen, okay, between source and sink flow. So pressure distribution in plane source flow, okay, again it's a plane source flow, so it is a point only, and the more important point here is it is horizontal. What does mean by horizontal? I'm considering a point, but it's not vertical like this. Okay, if I consider a point like this, then there will be effect of gravity, which is nothing but potential energy will be there if I use Bernoulli's equation. Okay, so but if I'm not using Bernoulli's, if I consider a plane source like this, okay, just consider this cross section, right, red color cross section, that is horizontal. Okay, if it is horizontal, this is the point, okay, source from which the fluid is emerging out. Okay, that is one point. Okay, that is the source. Another point I'm considering somewhere far away from this. Okay, we already know that if it is a source flow, there will be only what is that, radial velocity, tangential velocity will not be there, it is 0. So at source it will have more radial velocity. How it is? See this, V r into r is equal to k. We already know that k is a constant for a source flow. If k is constant, if r is minimum, then V r will be maximum. Okay, so if as r increases, as radial distance from the source, as radial distance keep on increasing, this VR value will continuously decreases, and it will reach one point far away. It will reach one point where the velocity will be almost zero, and that point is our reference point, which is also known as stagnation point. Okay, so very simple. As we move far away, okay, as we move far away from our source, radial velocity will be continuously decreasing, and at one point it will become zero. Okay, these are the 2 points. First point is I'm considering horizontal. Okay, that is source is like this. Okay, this is my source. If you look from this, if you project, that is, if you see a top view, then it will look something like this. Okay, this is not a front view. This is actually a top view. If you see in this direction, it will look like this. Okay, so from center, the force, the fluid will be emerging. Okay, so horizontal. Second point is as we move further away from source, far away from source, then there will be one point where velocity will become zero, because we know that radial velocity is decreasing with r. Okay, so velocity will become zero, and that point is I'm going to take it as a reference point, which is nothing but a stagnation point. Okay, now this is our general Bernoulli's equation. I'm not considering the potential energy because it's an horizontal, because potential energy will remain same in an horizontal line. Okay, and we also know that it is a irrotational flow. Why it is a irrotational flow? See, all the flows which we are considering from the beginning, I already said that if stream function and potential, if stream function and velocity potential function, if both has to exist for some particular flow, then the flow should be irrotational and incompressible. I said at the beginning itself when I am discussing uniform flow. So if the flow has to be, if the velocity potential function and stream function, if both has to exist, then the flow should be irrotational and incompressible. Keep that in mind. So if the flow is irrotational, then Bernoulli's equation can be applied between any 2 points in the flow field. We know that already, which I discussed in fluid dynamics. If the flow is rotational, I can apply Bernoulli's equation between only along a single streamline. If this is my streamline, I will apply Bernoulli's equation between 1 and 2 only. Okay, but if the flow is irrotational, you take whatever streamline. Okay, you take whatever streamline it is. I can apply Bernoulli's equation between 1 and 4. I can apply Bernoulli's equation between 4 and 5. I can apply between 5 and 3. I can do whatever I want. I can apply Bernoulli's equation between any 2 points in the flow field. Okay, so if it is irrotational, I can apply Bernoulli's equation between any 2 points in the flow field. Rotational, I can apply only along a single streamline. I already given this in fluid kinematics chapter itself. Sorry, in fluid dynamics chapter itself. Okay, now, so we know that it is irrotational. So simply what I'm going to do, I'm going to apply Bernoulli's equation between this source point, okay, between this source point and somewhere, or not between the source point, I will take some radial distance, okay, I will take a radial distance, okay, some distance r, okay, some distance r, this is the point which I am taking, okay, some distance r, okay, at some distance r, that point, and some point O which is present far away from the source, okay, which is present very far away from the source, but we know that the velocity becomes zero. But velocity only becomes zero, pressure is not going to become zero. So P naught will not be zero, but velocity will be zero. Why velocity is zero? From this consequence. If I apply Bernoulli equation between them, what will happen? Pressure at some radial distance, okay, pressure at some radial distance by rho g plus velocity at some radial distance Vr only, because there is no V theta. Okay, so Vr square by 2g. I am neglecting the potential energy, so which is going to be equal to, because it is horizontal flow, P naught by rho g. Okay, this is Bernoulli's equation between some point at some radius r and the point which is present far away from the source where velocity becomes zero. If I apply Bernoulli's equation between these two, I can obviously draw the curve which is needed, okay, the pressure distribution curve. First, how does radial velocity varies? As radius increases, radial distance from source, okay, radial distance from source increases, radial velocity is going to decrease. So if I plot it, radial velocity, let me plot it in blue color, okay, it's going to decrease, at some point it will become zero, okay, at some point it will become zero, that is, it will keep on going, at some point it will become zero. So this is radial velocity. As r increases, radial velocity is decreasing. Fine. Okay. Now we know that if r increases, okay, if r increases, VR is going to decrease. So if VR decreases, listen carefully, if VR decreases, what I can conclude about, I will talk with respect to this, okay, I will talk with respect to this. Simply, if this component decreases, then this component should increase, obviously, because the summation should be constant, right? The sum of this and this should be constant. So if VR decreases, then P should increase. Okay, if VR square by 2G decreases, then P by rho G should increase, then only the sum will remain constant. Obviously, that is a fact here. So simply, as R increases, VR is decreasing, so pressure should increase. Let us show it something like this. Okay, so this corresponds to pressure. Okay, so pressure will be keep on increasing as radius increase, as radial distance from source increases. Okay, so you need to remember that distribution. They might ask you in some 1 mark question. Further from this, I can do some modification. What I can do, I will bring this P naught by rho G to this side and VR squared by 2G to that side. So it becomes P minus P naught by rho G, which is equal to minus VR square by 2G. I can cancel this G, right? Very simple. And later I can bring this rho also to that side. So it becomes P minus P naught is equal to minus VR square into rho by 2. Okay, so again further this VR square, okay, can be written as K by R. Okay, simply VR square is K by R. So VR is K by R, so VR square will be K square by R square. So minus K square rho by 2 times of R square. Okay, so very simple equation. It's better if you remember this equation also, either this equation or this equation. It's simple, we are getting it from the Bernoulli's equation only. Okay, so as radial distance increases from source, pressure will increase, radial velocity will decrease. This is the conclusion which we are getting from this, and this is the final equation which we are getting. So next is sink flow. Okay, so what is this sink flow? We already know that instead of water emerging out of a point, if it is emerging inside, if it is going inside, okay, towards the point radially, okay, so it will be radially moving inwards, and that will also happen at a constant rate. So radially it will move inwards and it will disappear at a constant rate. So here also Q m dot will be constant, and obviously K will also be constant. And if you use the same logic, and you can derive psi and phi also. Okay, but here the one small change you will have is VR, that is radial velocity, will be minus Q by 2 pi R minus m dot by rho into 2 pi R, which is equal to K by R, where K will be taken as minus Q by 2 pi, that is including this negative sign I will be taking it for the sink strength, or similarly including the negative sign I will be taking it for the sink strength. Here K is sink strength, and that is why sink flow is also called as source with negative strength. They can ask this as 1 mark question too. Okay, so sink flow can be also called as source with negative strength, that is instead of flowing outside, the fluid will be entering inside. Okay, so source with a negative strength. If you take pressure distribution, the pressure distribution equation still remains the same. Why? Because velocity is negative, but we are squaring it. If you remember Bernoulli's equation, we will square VR square, so anyways the negative sign will go. Okay, so there is no that is not going to affect the equation. Okay, and finally all those things, you could see that everywhere, wherever negative sign is not there in source, here negative sign will be there, minus k theta minus k ln of r, and except this place where we will have the same equation. Okay, and similarly the pressure distribution also same only. So in this case also the pressure distribution, velocity distribution will look similar. As we are moving towards the center, velocity will increase and pressure will decrease. If I move towards the center point, velocity will increase, pressure will decrease. The similar type of pressure distribution as we seen in case of source.